So we're starting chapter 3 in our textbook, and chapter 3 is all about counting. If you remember, the point of a discrete object is that they are distinct or individual. That means that I can count them. I can lay them out on the table and decide how many there are. And our ability to count all of the objects that might be involved as input into a problem is really important for me to determine perhaps how many outputs there are to the problem, how many solutions there are. I distinctly remember every time we talked about truth tables, I wanted to be able to determine how many unique combinations there were of the input values. So if I had 2 variables, I would have 4 rows in my truth table. If there were 3 variables, I would have 8 rows in my truth table. So we want to be able to determine how many unique combinations that we can have. I'm going to give you another example. Let's say passwords. You are the network administrator and you need to be able to determine how many unique passwords I can have if, let's say for instance, your company allows passwords that are 6, 7, or 8 characters in length, that it can contain numbers and it can contain digits, but it has to have at least 1 digit. How many unique password combinations are possible? And that's what this chapter is about, is to show us some techniques that we can use to count discrete objects. So discrete probability can be defined as the number of desired events compared to the number of all possible outcomes. For instance, what is the probability of rolling a 1 on a fair 6-sided die? So I'm going to define a fair die as a die that is equally likely to land on any of the 6 sides with every roll, as compared to perhaps an unfair or a weighted die. Now you might say to yourself, this probability is pretty obvious because if it only has 6 sides and I'm trying to roll a 1 or any of the 6 values, I have a 1 in 6 chance of doing that. But let's see if we can clarify how I come up with that number. We're going to start with the cardinality of the event space, and we're going to divide that by the cardinality of the sample space. So the event space is all desired outcomes, but we want the cardinality, or the number of desired outcomes. We're going to divide that by the sample space, which is all possible outcomes, and once again, we want the number of all possible outcomes. So what is my desired outcome on rolling a 1 on a fair-sided die? Well, I want to roll a 1. There's only one way that I can roll a 1. I'm going to divide that by the total number of possible outcomes when I roll a 6-sided die. And it would seem like there are 6 different options that are available, or 6 outcomes that can occur. So that the probability of rolling a 1 on a 6-sided die would be 1 in 6. So what happens if I have 2 die? What is the probability of rolling 2, let's say 3s, 2 3s on 2 fair die, 6-sided fair die? So once again, I'm going to take the cardinality of the event space. I'm going to divide that by the cardinality of the sample space. Remember, the event space is desired outcomes, and the sample space is all possible outcomes. So the desired outcome is, let's just start with the first die. If I start with the first die, we decided that there's one possible way that I could roll. In this chance, we're trying to roll a 3. And there are 6 possible outcomes. With the second die, there's also one possible way that I can roll the second die. There's also one possible way I can roll a 3 on the second die. And on that second die, there's only 6 possible ways that I can do that. This is going to give me 1 times 1 divided by 6 times 6, which is 1 over 36. So there is a 1 in 36 probability that I will roll 2 3s using 2 fair 6-sided die. So let's see if we can apply this to other discrete outcomes. How about, what are the chances of rolling a 7 using 2 fair die? So this is going to be a little bit different than trying to get a matching pair, because now what I want to do is I want to find all possible ways there are for me to roll a 7. Remember, I need to take the event space, which is the desired outcomes, the total number of desired outcomes, divided by the cardinality of the sample space, which is all possible outcomes. And for our purposes, desired outcomes are rolling a 7. So that begs the question, how many different ways can I roll a 7? Well, I'm going to use them as ordered pairs, and I'm pretty sure that if I have 2 die, I can roll a 1 and a 6. I can roll a 2 and a 4. So how many different ways? So how many different ways do I have to roll a 7? We have done ordered pairs, so I'm going to say that this is the set that is going to contain, I can roll a 1 and a 6, I can roll a 2 and a 5, I can roll a 3 and a 4, and then I can also roll, because I have 2 die, I can also roll a 4 and a 3. These are going to be a separate set because I have 2 die. Then I can roll a 5 and a 2, and I can roll a 6 and a 1. So we need the cardinality of the number of all possible outcomes. We've already decided that since I have 2 die, it's going to be 6 ways that I can roll the first die and 6 ways that I can roll the second die. If I count up the numerator, there's actually 6 different ways that I can roll a 7, and there are 36 ways that I can roll 2 dice. So I could actually reduce this to 1 and 6, which means that there is the same probability of rolling a 7 on 2 die as there was rolling a 1 on a single die. Now for this ordered pair, the order in which the numbers appear matters. That's why I can roll a 1 and a 6 and a 6 and a 1. Those are 2 different rolls of the dice because I am using 2 separate dice. So with a 1 and a 6, the 1 could come up first. But if I have a 6 and a 1, the 6 could come up first on the first die. So we can apply this probability to other games of chance, such as card games. Let's say, for instance, that you're playing poker. What is the probability of getting 4 of a kind? If a standard deck of cards has 4 suits and there are 13 face cards in each suit, what are the probabilities of getting the same face card in all suits? It also works for lottery. For instance, in the Powerball, what are the odds of matching the Powerball along with a certain number of values? Here's another example of the odds of winning, or the probability of winning. So what we need to do is to be able to figure out how many different desired outcomes are there and how many different possible outcomes are there.